So welcome to my video on infinity. First, I'd like to apologize for the amount of times I'm actually going to say infinity, but anyone who's been down this rabbit hole will know that's what inherently happens when you do. You may remember from my previous video, I talked about bounded and unbounded infinities, and I want to show you how I believe that you bound an unbounded infinity. Now, if you take an infinite line, obviously, it has some strange properties. It goes on forever in both directions, and you can bound it off anywhere you want on it, and inside that boundary is also going to be infinite. Now, if we take 0 to 1, I call this a full infinity because it's full of numbers, full of positive numbers. But what you really want to get a true essence of what infinity is that you need to have the negatives in there. So here's negative infinity to positive infinity. The reason why this, for me, is better is, one, you have an integer. You can find 0 in the middle of it. And secondly, it's an empty infinity in the fact that all the negatives and the positives cancel each other out. And this has some advantages that you'll see later on. Now, 0 and infinity share a lot of characteristics, but they're the complete opposite. One's nothing and one's everything. But they are boundaries or limits, whatever you want. So I'm going to clump them together and start just calling them singularities. So the first observation is that if you want a full infinity, you need at least 2 singularities. If you want an empty one, you're going to need 3 singularities. Now what I'm going to do is something crazy, and that's put infinity on the number line. It's not too crazy. People have done it before. And it's just as crazy as putting 0 on the number line. People thought that was insane for hundreds of years. So why not just put infinity on the number line and see what happens? So here we go. Let's see, nothing crazy happening. We're all going to be fine. But what else can we do with this? Well, we can assign the positive and negatives to these, right? So here we have the 0, and on this side is negative, and this side is positive, and here's positive infinity. But what else can we do? Remember, I said these are singularities, and I want them to have the same properties. So I'm just going to assume that just how this 0, this singularity, flipped the number line from negative to positive, infinity here, or this singularity, is going to flip it from positive to negative. And so there, we don't even need the infinity symbol anymore. We can just make it a 0 with the signs flipped, which to me is a much more coherent way of thinking of infinity, because it's the same, but it's the opposite of 0. So now that we've preserved this property of the singularity, it's kind of obvious what goes next, right? We've done this before, like we've used omega, w plus 1, and all these things, but to me, that is just too much. Notation can be a lot easier by just saying that these are negative. So this is the highest positive number, and this is the highest negative number. Just like this singularity, this is the lowest positive number, and this is the lowest negative number. So it goes positive, then it flips to negative. Now this has, and then obviously eventually this is going to get back down to 0, where it's going to flip. Now this explains a few things. First, this explains that this is symmetric in both ways. You can come at this from both ways and it's the exact same. What else this does is that it can repeat on forever, and they all cancel each other out, and this shows how you can fit an infinite amount of things inside a finite space, or that you can have an infinity that goes on forever. So how do we bound this infinite line? Well, obviously we can bound it however we want, but let's go with 0 and 1. Now, to me, this is a full set. It only has 2 singularities. It needs a 3rd singularity to make it an empty infinity. So how do we do that? Well, we can do it any way we want, but one way is to include -1. Now you have all the negative numbers and all the positive numbers, and there's your singularity in the middle. Another way is just to add a singularity. So that would mean the first half of the numbers in 1 are positive, and then the second half is negative. Now, to me, this makes intuitive sense, because if you look at numbers, you see the growth goes up, and the growth goes up, and then it just shoots back down to 1, right? Because these are all equivalent. These are all 1. So the value goes up, and then it shoots back down to nothing, then it shoots back up. I never agreed with that. It just seemed very unintuitive. But if we add singularities in between each number, you get a much more intuitive way of how the numbers work, right? They grow up, then they go negative, then the positive and negative, positive and negative. But this is just one way of doing it. You can have as many singularities as you want. You can have it on 0.1, 0.2, 0.3, 0.4, as long as you have the negative numbers in there somewhere. Okay, you can't just have all positive. So how does this work to graph it, right? 1 over x. So you have your graph, obviously. You have your 0 right here. But you gotta remember, this 0 is polarized. It has a positive on this side and a negative on this side. So your positive would come down here, and eventually it's going to hit infinity, and it's going to cross this line, and it's going to go from positive to negative. And then eventually it's going to go down again, and it's going to hit the next one, and it's going to flip signs again at this one, and the negative one does that. So in 2 dimensions, you can make this graph have an infinite amount of zeros going all over there, and these lines are going to go flip back and forth from 0 to infinity. So why do I like this form of infinity? Well, first of all, it explains how you can fit an infinite amount of infinities in an infinity. Second of all, it shows how there's an infinite amount of infinities. Also, it can be written cyclical or in a circle like this. So you can have it, this takes actually an even amount of singularities, as you can see like that. You can put as many singularities as you want. It always wraps around. Just many cool things like that. To me, this also explains why you can have negative and positive square roots of things, because you don't know where it's going to end up. Because remember, it works both ways. So you don't know what side it's going to end up or where the singularities are on each number line. This way of doing it is also very good for symmetry, right? You can't tell the difference between going left and right. This way of writing infinity is perfect because it's the same, but the opposite of 0. And also, if you take any bounded thing with 3 singularities and divide it up, you can see that this infinity and this infinity are the same. They're just opposite from different directions. And lastly, I think this is a good way to think of infinity because it may give insight into how the Riemann hypothesis works, right? For me, the whole Riemann hypothesis is taking this unbounded infinity and flipping it and rotating it somehow through this bounded infinity. And what spews out is the ratio of the primes. Remember how I said the unbounded infinity gives you the integers. And when we put it through the bounded infinity, we end up with ratios. And because this is I, this infinity is upside down. So the 14 of the first 0 is actually the last prime number, and the next one is the second last prime number. And that's why they get closer and closer, because it is the prime numbers flipped upside down. But it's not accurate in any way because they're only the ratios. We've lost all the information about the integers. And the reason these all end up at a half is because the integers go through the bounded infinity. So say for 2, it takes us 2 jumps, goes through the halfway point of 1 and 0, and then comes out the other side. And 4 gets eliminated because it just is redundant. And all the prime numbers make it through, the information of the prime numbers makes it through the singularity between 1 and 0. And that's how we end up with these ratios. All right, thanks for watching.